Hello everyone and welcome back to my channel Gyan Sampada. In our previous class of magnetic resonance, we discussed about NMR, that is nuclear magnetic resonance. And we saw that based on the radiation which is absorbed, we are going to distinguish mainly two different types of resonance phenomena. One is ESR and another one is NMR. So ESR, that is electron spin resonance, we have already discussed in our previous class, and today our class will be dealing with NMR. So as told earlier, the principle and working is almost same in both the cases. However, the application is going to differ. So if you have not gone through the previous class, then first go through it and then continue with today's class. So let's start our today's class, which is mainly based on nuclear magnetic resonance. And now let us move on to the derivation part of it. So we are going to see some of the equations and understand in detail about this. So here we are going to consider the fixed coordinate system, and in fixed coordinate system the equation of motion of nuclear moment, which is denoted as mu, with angular momentum generally denoted as capital G, in the field H, that is the static magnetic field, will be dg by dt is equals to mu cross H. So this is the equation of motion which we have already seen in detail. There we had dg by dt is equals to gamma g cross H, and we know that gamma g is nothing but mu. So we have written dg by dt is equals to mu cross H. So remember, whichever letters are in bold, they mean they are the vectors. So this is the magnetic moment vector, H is the static field along z direction, G is the angular momentum vector. And then we are going to consider second coordinate system, which is rotating about z axis, and its corresponding angular velocity is omega. So two coordinate system, one is fixed and one is rotating about the direction of applied magnetic field. So in that case, we say that rate of change of angular momentum g in a rotating system, which we consider as dg by dt whole star, is related to dg by dt, that is the rate of change of angular momentum in fixed coordinate system. So both are interrelated, and the relation is given as dg by dt is equals to dg by dt star, that is fixed coordinate system, is equals to dg by dt in rotating coordinate system plus omega cross g, and we are calling it as equation number 6. So now if we make use of these two equations, that is putting equation number 5 in equation number 6, then we can say that dg by dt star will be equal to dg by dt minus of omega cross g, and instead of dg by dt we are writing it as mu cross h from equation number 5. So this is equation number 7, and we already know that gamma into g is equals to mu. So gamma is gyromagnetic ratio, which is nothing but Ge by 2mc, what we have seen in the previous classes. So mu is related to G. So just making use of it. So instead of G, we will write it as mu by gamma. So if we take mu common outside, we can write it as dg by dt whole star is equals to mu cross H as it is. Instead of minus, we will be having plus, because we are going to interchange omega and mu, and we are remaining with omega by gamma. So G is equals to mu by gamma, that is omega cross mu by gamma, which is equals to minus of mu cross omega by gamma, mu taking outside, we are remaining with this equation. And if we compare it with equation number 5, we can see that we have mu cross H, and here it is mu cross H plus something, and that we are going to write it as He. So He is the effective field, which is equals to H plus omega by gamma. Let us call it as equation number 8. And here when only applied field is steady 1, that is h along z direction, and when omega is equals to minus gamma h, we can say that HE will be equal to 0. So just we have substituted this value here in HE. So H plus minus gamma H by gamma. So gamma gamma will get cancelled. H minus H is 0. So effective magnetic field will be 0 when we have steady applied magnetic field that is acting along Z direction. So what is the significance of it? So according to this we can say that there is no torque which is acting on the magnetic moment mu in rotating frame, which means that the magnetic moment mu will remain fixed with the time in this system. So even if you consider rotating frame, then also mu will not vary in case of rotating frame. So these are the things where we have just applied the magnetic field. So due to magnetic field, splitting takes place and we have seen mu is going to remain fixed with respect to time. And then if resonance has to take place, means with magnetic field we need to apply alternating field also. So applying a field of magnitude h1 along x-axis, and that field is going to be rotating about z or z star axis. So z is with respect to fixed coordinate and z star is with respect to rotating frame. So the applied field of magnitude h1 will be rotating about z axis with certain frequency denoted as omega, in addition to that of h, which is the static magnetic field. So due to the alternating field, we say that the equation of motion is also going to change. So we can write the new set of equation of motion as dg by dt star is equals to gamma g cross Hez plus h1. So same equation, LHS is this one, gamma g is nothing but mu cross, instead of He we are having Hez plus h1. So there is a additional field which is acting along x-axis. And now this totally can be taken as the effective field. So this is the new equation of motion denoted as equation number 9. And now if we look at this He, then we can say that it is having certain components along different directions, that is along x direction, y direction and z direction. So along x we denote it as He x star is equals to h1, because we have applied the alternating field along x direction. Then along z direction Hez star is equals to h plus omega by gamma, which we have seen in previous slide. And along y direction voltage will be developed but field will not have any component. So Hey star will be equal to 0. So these are the components of this final effective field, that is after application of both fields, that is static as well as alternating field. So when we are having the components, we can write down what is the effective field, and it is found that the effective field is constant and its value is He is equals to square root of Hez square plus Hex square plus Hey square, that is each with the stars. Then we just need to substitute the values of these. Then we get He is equals to square root of h plus omega by gamma square plus h1 square. So this is the effective field, and if we consider the angle, then angle with z axis along which static field is applied will be tan theta is equals to h1 divided by h plus omega by gamma, that is x component divided by z component. So if we need to visualize, let us consider static field H along Z direction and alternating field H1 along X direction, which is nothing but HEX star. Then we can observe the precession of magnetic moment in rotating coordinate system. So the angle here is alpha and the effective field is given something like this, which makes an angle theta with the Z direction, and this is the amount of HEZ and this is the amount of H1. This vector may be magnetic moment or even the angular momentum because both are related to each other. And this is the derivation for NMR phenomena, where we have found out the equations of motion and also derived the components and denoted it even graphically for easier visualization. And finally, moving to some of the points to remember. As such, we know that NMR, that is the nuclear magnetic resonance, is a selective absorption of very high frequency radio waves by certain atomic nuclei, means protons are involved, that are subjected to an appropriately strong static magnetic field. So as such, many nuclei have spin and all nuclei are electrically charged according to NMR principle. And the energy transfer from the ground energy to the higher energy level is achievable only when an external magnetic field is applied. And the main thing is that here nuclei of atoms are involved and not the outer electrons as in case of ESR. So instead of electron we are having nucleus or proton in case of NMR spectroscopy. And the second difference is that here radio waves are interacted and they are absorbed by molecules, causing nucleus to spin flip from one orientation to another. So in previous, that is in ESR, we had microwave frequency which will be absorbed to show the resonance, and how it works we had seen. So when we apply the magnetic field, what happens to the electron, in the same manner it will be with respect to proton. So spin flip means as you give the alternating field, the direction of magnetic moment is going to vary, which we had seen as alpha and beta states in our previous class. So working principle remains the same, but only the difference is the absorption of radiation. Earlier it was microwave radiation and in NMR it is radio wave frequency. Then the NMR spectrometers use a very powerful magnets to create even small but mainly measurable energy difference between two possible spin states. So if we consider two spin states, then a small amount of energy difference which are measurable can be found out, for which a very powerful magnet is used. So these are the points which you need to remember when you deal with NMR. Then moving to the applications. As such, there is a widespread application in all the fields of science. It may be physics, chemistry, biology, life science, anything. So as such, NMR is used to determine the structure of organic molecules in solution, like the structure of proteins, water or fluid in the body, etc. That is, the NMR is also used to identify and quantify the metabolites in the food, which is a very important thing. Then NMR is used to study molecular physics, crystalline and non-crystalline materials. And finally, where generally we observe it is the MRIs, which is an advanced medical imaging technique where any flaws in the human body can be easily understood. And the principle behind magnetic resonance imaging is NMR itself. So these are some of the broad applications of NMR. As such, it is having a vibrant amount of applications. So these are some of them. As it is a type of methodology, there will be some merits as well as demerits, but for time being, these many points, the working principle, the arrangement of the apparatus and the application is enough. So I hope you got some of the main details which generally won't come into picture in case of NMR, and I hope it was helpful for you. So today we have studied about NMR and previously we have studied about EPR. Just go through both of it, compare those so that understanding becomes more easier. So these are some of the details about NMR, and see you in our next class. Till then, stay tuned, study well, practice more and more, and thank you for watching.